Okay. You're on next, Rashid. So we'll fill the bottles up for you. Good.
Just put it over the head. It's that way. It still looks so serious. Is that okay? No. I always do it the wrong way. I go that this way? Yeah. She said the other way, so who is correct? Okay, does it work? This is funny. This is funny. Are you sure that's the right one? You know, this is always a good sign when you start with problems. Is that okay? No. It's okay? Thank you. It's that way. Here. Oh. Okay, so so after Keith's talk about policy management and so on, I'm going to talk bioeconomics and how indicators can feed into bioeconomics. So my goals for you are two, very simple. I'll present a simple bioeconomic model, and then I hope to, I hope to also then move ahead and show you a simple indicator that we are currently developing, we're working on right now as we are talking. So that you see how one can feed information into a very simple indicator. Yesterday you saw complicated ones, really difficult ones, composite, and you also learn about the pitfalls that can come. Today I'm going to show you such a simple indicator you're going to go after me again because it's too simple, okay? So that's that. That's the goal. What is a fishery? This is my caricature of a fishery. I love simple models, guys. So this tells me a lot about a fishery. It's made up of two components. You have the natural side, and then you have the what? You have the human component. And actually, and I like to say this when I'm talking economics to mostly biology classes like yours. The only reason we have this big problem with fisheries, if you agree that there are problems, is because people go to the fish, right? It's because we do this. We go to the fish. If you leave the fish alone, they know how to take care of themselves, right? So the issue of fisheries management is actually about managing the human component. So if you look very closely, we don't really need biologists. No reaction from you. Come on, you guys are nice. I said this somewhere and they nearly chased me out of the class, right? I said, we don't need biologists. All we need are economists, social scientists, lawyers, and so on. And then get out of here. So I said, okay, we actually do need biologists, but only for basic information to help us manage the fishery. They got even more angry, right? So really, yeah, we need both sides, definitely. And that is, I think, the purpose of IMBER. This is what IMBER is pushing. How do we bring the two together? And you see a very simple model where this is actually done. And what is this model? That's it. I tell you, I like simple models. I'm hoping that just looking at this, you know a lot of what is already here. This is the kind of model 50 years from now, you guys will remember, right? And actually, if you remember these two models, in my view, you already know all that you need to know about the biology of fish and the economics of fish. you can go to sleep, right? Isn't that cool? The rest are details, frankly speaking. They're details. And that's a biological model. If you're looking annually, each year at the beginning of a year, 1st January 2014, there is some amount of fish in a given system, right? And that is always true, right? And that includes zero. You can have zero fish in the ocean. So you have that. And as the year goes, you are going to get some growth. These are living things, they are renewable. You know, so you will have growth, and there will be some recruitment. Some new fish will come in, everything being equal. You know, there will be recruitment. Some will die, It's the nature of things. Some will die, some are born, some will die. And because we like to eat fish, some will be caught, right? And frankly, that is all of biology in one line. Biologists come after me, come on. That's all of it. The rest is details. Of course, you need to know about habitat, you need to know about climate, all those things, but that is really to help you understand these dynamics. All right? How about economics? Economics is even simpler. I learned all the economics I needed in grade school. When my teacher told me, you know what? Profit is selling price minus cost price. Done. Go to sleep. That is economics. I say this in an economics department, they also try to chase me out, right? But really, that is it. The rest is details. It's details because to really do this for a fishery is tedious, and I can tell you that. But really, if you go home with this is something you can remember for 50 years, and you are in good shape, okay? So that is a bioeconomic model builds this economics on top of the biological model. Voila, it's done. Okay, now, but of course there are details, and just to give you a little bit of that equation, so if you take what we call rent, it's actually the first element of rent is the revenue, right? That is what I was telling you, selling price. If you are looking at the unit of a good, you're talking about the revenue. And the P is the price per unit of fish you sell when you catch them. So price. H is the quantity you catch. And the second element on that side is your total cost of fishing, right? So you take out a number of fishing effort, one boat, 2 people on, you go out. It costs you something to take them out for a given period. And that C is the cost per unit effort, right? So then you have the total cost, you have the total revenue. The difference is your economic rent, if you are talking of a whole system, a whole society, right? Or profit, if it's a private business. So the difference between rent and profit is quite close. I just make it, if you're talking about private business, they talk profit. If you're talking of society, you're talking about the net benefit and the net cost, and you get economic rent. So that will just give you a simple. So that is the R. Now, Schaefer-Catch equation. Some of you, many of you will know this, and you don't know that. This tells you what you need to catch the fish. So the Q is the technology you take to catch the fish. It's called catchability coefficient. It's the amount of, if the proportion of fish, of the biomass you can take with your fishing technology in a given period. So it tells you about the technology. You have a small boat, I have a big boat. My Q is likely to be larger than yours, right? So that is that. Then you have the E, that's the effort, amount of power you take out to fish. And X is the quantity of fish in the ocean. So that's our model of fish catch. Another very simple model. You can see I put there. This is highly dubious. And this relates to some of the discussions and the points I've been trying to make yesterday. In fact, I think 90% of all bioeconomic models of fisheries use this equation. And we all know it is wrong, right? Yeah, you go and estimate, it's almost never like this. There are coefficients on the E and this on the Q, right? Because the relationship is not one-to-one. Because what this thing says is that given your technology, if you have one more biomass, unit of biomass, you can catch some amount of fish in a linear way. And the same thing with the fish and the effort, right? And this is not the case. People spend all their life trying to estimate this. But actually, even though it's long, it gives you good insights about the fishery. And this was partly what I was trying to say yesterday. So you can be totally wrong and still give insights, and I really believe in this. So that is a good example of that. So that's what we talk about here. All right. What do we do with this? This figure, please remember this figure for the rest of your life. This is the basic bioeconomic model. It's static, so it's far from being the full thing, but it tells you a lot. So here, you have your total revenue, TR, and your total cost, TR. So this is dollars. The more of it you have, the happier you are, everything being equal, right? Some people get sad when they get money, more money. Is there anyone in this room who gets sad when he or she gets more money? No, not in this room. You guys are too rational, right? Actually, there's no place where I ask this question and I see somebody raise their hand. Honestly. So actually, it's a good assumption, right? So here you are. And here, this is the amount of effort you take out. That's your fishing effort. And this thing here is the total revenue, which depends on the effort you take out and obviously depends on the biomass or the biology of the fish. So if you had biomass on this axis, this is actually the yield you can get given the fish you are looking at. Some are very productive, some are not. So this curve will be like that or whatever, depending on the fish. Now, that is the yield. That's the surplus growth in each year. So if your effort is here, right, that's your effort, then this will be the total dollars you can get given the fish you are looking at. And the total dollars, I told you, is the price times the catch. So that's your revenue curve, depending on. If you take too much, if you take too much effort, see what happens to your dollars. After some point, more effort doesn't do you any good, right? And if you remember on the first day, actually, when I said your catch increases and stabilizes, meanwhile your effort is going, waste of resources, really. That comes from the theoretical model. So in any event, if your goal is to maximize your economic benefit, your money, you never want to exceed this point. And that is what we call the maximum economic yield, the effort at maximum economic yield. Why? Because that is the place where you have the largest gap between your revenue and your cost, right? If you move anywhere, if you move this way or that way, you are going to leave money on the table. Economists don't do that, right? Actually, some of them do. but so that's the point. This is where you want to be. Now, this figure is very, for example, if your goal is food security, people have argued. That's why the biologist maximum sustainable yield is so popular. In all UN things, we're always talking about MSY, because they are thinking more fish. If your goal is to have the largest amount of fish year in, year out, this is what you go for. But economists will say, okay, if that's your goal, we'll let you do it. But you are leaving money on the table. And our friend from Tanzania, he took me to task, you remember? And so your first graph says we'll get more fish. Your second graph says we'll get less money. Why? They are catching more fish, but you get peanuts for it because it's not valuable fish in the market. So that's the difference between that. Actually, some social scientists actually argue that, why not here? Because you can employ more people, they say, right? So the objective is important in this. But that's the basic bioeconomic model. The rest of our models are really, you make this dynamic, you make it multi-species and ecosystem, and it gets more complex. But the underlying model is this one, nothing more. This thing, anomic equilibrium, that's just a name for the point where your total revenue is exactly equals to your total cost. Yeah, so at that point you are not making money. And the thing is, if you don't manage a fishery, the tendency is to get here. Because if you are here, some will see, oh, there's still money to be made, right? It's a gap, so they keep coming in. And if you exceed here, you don't want that because you'll be losing money. When will you choose to move away to this way if you're a fisher? Under what condition will fishers fish this way? Subsidies. Yeah. If the government is paying some of your cost, yeah, you can move here. So if you have subsidies that takes this thing down that way, then of course they will be here because they are making money still, right? And more people come. That is the theoretical basis of most of my papers on subsidies, right? So that's what I told the member of parliament. If you want to manage it sustainably, you don't do that because it's too late to more effort coming in. All right, that's the basic bioeconomic model. But this is static. So if you want to go dynamic, which you have to really if you're talking about fisheries, because they are renewable, right? What you do today will have consequences for you tomorrow, right? Good or bad. So you need a dynamic model. And in general, this is the equation we try to maximize in economics. And it's not very different from the static equation I showed you. The only thing is that you have time indexed to your total revenue, which is V in this equation, and time is indexed to your cost, which is T in this equation. So each year, how much do I make? How much does it cost me to make this? You get the gap. Next year, you do the same, right? So you have a series of net or rent each year. And then for you to be able to gauge how profitable the future is likely to be, you will need to add these values, right? But in economics, you don't just add dollars like that, right? Because the dollars coming to you today are more valuable than the same quantity of dollar that will come to you in 5 years. Do you agree? Do you agree? So let's say I have $1,000 to give you, or you have $1,000 to give me. That will be much better, right? Okay, I have $1,000 to give you, and I say that I can give it to you today, or you wait, I'll give the same $1,000 to you in 5 years. What will be your choice? You want it now, you see? So, and why do you want it now? It's because it's more valuable. It's done than tomorrow. And that's a discounting concept we'll get into. So because of this reason, everybody wants their dollars today rather than tomorrow, right? So that if you have a flow of dollars coming, you can't just add them, because they're different dollars. So you have to do something we call discounting. You have to reduce the future money to its value today, right? And that is the concept of discounting in economics. Have you heard about discounting before? I should have asked this question. A few years ago, I gave a lecture to new professors from science, engineering and science at UVC. And the topic was discounting, economic discounting. So when I went in, the first thing I said, has any of you heard about discounting? And one guy, very confident, oh yes. I said, what is it? I said, when you go to Walmart. yeah, so that was what came out of it. This is more serious than Walmart discounts, okay, guys? This allows you to collapse flows of values into today's value. So we call that net present value, that's MPV. So discounting is important, and I'll get back to that. So that is all that I'm going to talk about on bioeconomic models today, no more. And if you can remember this today, tomorrow, 5 years from now, I will be a happy guy, okay, guys? Really. So that is that. This is a dynamic version of the static one. Now, let's go into the second part of my talk, which is we set out, me and William Chang. This is really crazy, right? I should have put it off of the Skype is. So here we set out to develop an ecological economic indicator for fish vulnerability. You know, biologists talk about this, ecologists talk about fish vulnerability all the time. So one day, William, that was William Chang, some of you know him. That was his PhD thesis, was all about. And then one day I said, William, this vulnerability thing, it doesn't tell the whole story. It's just looking at the biology of the fish and talking about vulnerable. How about the fishes, you know, right? So if you have a fishery where there's no fishing, if it's the same stock, and another place where it is fish, are they equally vulnerable? Of course they are not, right? So that was the beginning of this idea, to try to explore how economics through integration with ecology can be used to provide an index that is a more bioeconomic index of vulnerability. And even after doing this, we actually haven't taken the whole thing. The social scientists, anthropologists will say, how about the social side? So you can build this into a bigger monster. And then a lawyer will say, this is all rubbish if we don't have a good law and so on. But at least we move it just from the ecology to the economics, okay? So, and this is a major point I want to make, because when I start showing you maps, before you jump all over the table, please remember this. What we are doing here, we are not looking at how effective management is. It's not in the model. We're just looking at the fish, and we're looking at the drivers of fishing and trying to say something about how vulnerable a fish stock will be. That's the first step of our work. The hope is to have a series of actions, and one of them will actually see how do we incorporate effective management into this, okay? So please remember that. So if I show Iceland not doing good, I'm not taking into account that they have ITQ systems. I'm just looking at their fish and the drivers of fishing. All right. So, two important concepts. Conservation is about ecology, right? You want sustainability. So that's the biology side as we formulate it here. And we just use only one parameter of life histories to do this simple indicator. It's crazy. Yeah. So we just look at the intrinsic growth rate of fish as an indicator of their life history. It's not broad enough. This is where arguments start. It's too simple. Yesterday it was too complex. You were not happy. Now I'm talking about a simple one. But really, so that's just really simple at this stage. And so life histories, mainly intrinsic growth rate. And we collapse all the economics in the discount rate. Essentially, we're saying that how you value today and the future is a good measure of your economic pressures and whatever is making you go to fish, you see. So if you have subsidies, you have the ability to catch the fish more now than tomorrow. If you have bad management, then if it's open access, actually your discount rate is infinity, right? There's no tomorrow. So we just absorb all this in that single indicator called discount rate. Very brave, isn't it? Yes. So that is essentially what we are doing. And the basis of this comes from actually old theory, if you like. Colin Clark did some work here in 1973 when many of us in this room were not born, I guess, right? So this is old theory. But so what we are doing, we take an old theory and put life into that through data and so on. So this is what Colin Clark says. And another crazy assumption says, if you have a fishery where the cost of catching the last fish is lower than the price of the fish, then these two conditions hold. Do you picture that assumption? It's a very strong assumption. You can almost not see it anywhere in real life. But if that were to happen, if the cost of catching the last fish in your ecosystem is lower than the price you will get for catching that fish, then you will overfish your stock. Even if you own it as a private owner, you will overfish it when the discount rate you get is greater than the intrinsic growth rate. Okay? And actually, you can drive your fish to extinction if the discount rate is 2 times, at least 2 times of the intrinsic growth rate. Well, Clark is a mathematician, applied mathematician, UBC. He's over 80. He's still writing more than many of us in the room. It's amazing. So he did this, and you can find science. Everybody knows what science is. JPE is the Journal of Political Economy. So he published them, and this is a message for you. You don't only publish, you republish. Huh? To be a really big scientist, you republish. So he published this in Science because actually the audience of science are quite different from the audience of the political economists. So he packaged them for these 2 big journals and got them through. So it is very influential because both groups actually know about this. So that is the theory upon which our empirical work that I will be showing you was based on. Now, these equations, as you have them in mind, the implication of Clark's idea is that fishes, economically rational fishes, make this calculation. They say, hey, each morning they say, okay, I have some fish in here that I can catch today, or I can leave it tomorrow to catch next year or tomorrow, right? Which one will give me the most? Should I catch the fish? If I catch the fish now, will I get more money versus if I leave it until tomorrow, and vice versa? So that is the thinking in the head of the fisher according to this model, economic model. So that's it. The rational portfolio manager will cash out if the resource, will cash out the resource and invest the proceeds elsewhere. So if you know that you make more money by catching the fish today versus leaving the fish until next year, you will catch it now. Why? Because you can invest it, right? You can use it to support your daughter to go to school, or you can use it to buy shares of Google, right, which grows 10 times than the fish grows, right? So you will do it. Very intuitive. Simple model, powerful, really. Except if you have arguments that this is not true. In fact, a few years ago, Serge Garcia is a big FAO guy, many years. He's retired now. When he started his career in the 60s, he went to Senegal. And there was lots of activity, fish coming, very lively. Then he goes at the end of his career in 2000, and the whole place was quiet. No fish, no activity. So he saw this guy sitting under the tree, an old man. He went and started conversing with him, and he said, "Sir, what is happening? I came here in the 60s, and I believe by then you are a young man. There was so much activity here, lots of fish and people, and nothing is happening here. So what happened?" And the old man had a big laugh. Ha, ha, ha. He said, "You see, look here. You see all the houses there? All this, that is the fish. That is the fish." And that is Colin Clark, actually. They've converted the fish into houses, right? So this model, I think, is quite powerful. And when we do it, we check this out, the northern spawning herring, we nearly lost it. And people have looked at the economics. Actually, what they did is rational. Huh? And I have looked at this with Ansel Cameron, and actually the northern cod stock that fell, if you do the discounting economics, that is the right thing they did. They made more money than keeping it. So that is some real applications of Mr. Clark. So we say, okay, given this, I'm sold. Some of you may not be sold to this, but so what can I do with this to help fisheries management? And that is how we started developing this index. Now, you guys are going to kill me for this. Now, I don't want to